Okay, here we'll look at this again as this is part 3 video for assessment methods, and here is a description of differences that you might find between models that are lump models versus distributed parameter models. And I've got two tables here, one on this page, on this screen, that just shows level of detail going all the way from what we might call generalized to mid-level to detailed. Generalized might be watershed size. Mid-level might be where we've subdivided the watershed into some homogeneous areas, either sub-watershed or maybe hydrologic unit areas. And then detail would be where we might subdivide the watershed into a grid, either rectangular or triangular or some other type of polygon grid. And here, this table associated with the detail for simulating runoff, just surface runoff simulation. And for the generalized case, we might have something where we just say, have a ratio of the amount of rain that is converted to runoff. So there was a method in hydrology called the phi index method, where you assign for a watershed what fraction of rainfall becomes runoff. So if you said that the phi value is equal to 0.2, then that would mean that for the watershed as a whole, 20% of rainfall that falls on the watershed would become runoff. There's no detail in that about how the runoff is distributed over time. There's no detail about the effect of rainfall intensity on the runoff generation process. So it's, you might say, a very crude way of representing a runoff, and it's for the whole it's for a whole watershed area. The second level of detail might be what we call the mid-level, where you could use something like a curve number to represent the runoff from a particular soil type or soil series. So the soils for the whole United States have been classified into soil series, and the certain soil series would have a curve number associated with it. And with this, you're able to calculate how much runoff would be generated from a given rainfall and from a particular storm event. Again, this method does not show how the runoff is distributed during the rainstorm event. It only tells you, basically indicates to you or calculates for you how much runoff is generated from the amount of rain that falls within a particular rainstorm. And then a more detailed representation would be where you use an infiltration equation to calculate the infiltration process. And for this, you would be calculating the infiltration at a point in a watershed. So let's say for a grid-based method, you would have a grid cell that has a certain size, maybe 10 meter by 10 meter, 5 meter by 5 meter, even down to 1 meter by 1 meter grid cell. And the soil properties in that grid cell are well defined, and the infiltration process would be simulated with a infiltration equation that would determine the rate, the amount of runoff that is being generated during the rainstorm event, not just how much occurs for the entire rainstorm event. So again, just a matter of what kind of detail. So the lump parameter model would be more at the top of this diagram, or of this table, more generalized, and the distributed parameter model would be more towards the lower part, the detailed type model. That is for in this case, for simulation of surface runoff. We have other processes going on, and so this next table is just talking about or referring to the other processes going on, such as, again, infiltration, erosion, pollutant transport, and that sort of thing. And here, the scale of the operation or the detail of the operation is given as columns, where the type of process is the first column, and then the scale at which it's looked at is given as the second, third, and fourth column. So case of generalized versus mid-level versus detailed representation. So, for instance, land use in a generalized model might be that you would differentiate between agriculture, urban areas, suburban areas, forested areas, and so forth. Whereas mid-level would break down agriculture not just as, would just a general representation of agriculture, but would have cropland, forage land, and so forth. That so you'd be able to subdivide that way. And then a more detailed level might be where you actually don't just say it's cropland, but you would say, well, we've got corn here, we've got soybeans over there, you've got ridge tilling in the corn, you've got no-till in the corn. So you've subdivided the area into more specific details. The lump parameter model would be more likely to the left in this table, the more generalized kind of representation, whereas the detailed one on the right would be associated with the distributed parameter model. So how do we go about selecting a model for our particular use? And these are, I've got listed here some criteria that we might consider in making that selection. So first we want to know whether a particular model will provide the information that is needed for your particular application at hand. So if what you want to know is just the average runoff out of a watershed or the total load coming out of a watershed, it may not be necessary to use a distributed parameter model. You may be able to get the information from a lump parameter model. And so that would automatically help you to make a selection as to which type of model you're going to want to use. A very important step would be to determine whether a model has received adequate testing. There are many models that have been developed by different individuals or by state agencies, federal agencies, and so forth. And not all of those models have received a large amount of testing. The ones that have received a large amount of testing are the ones that have actually come forward as being the ones that are recommended by the EPA, by the MPCA, and other agencies for use in environmental modeling. The question is about ease of use. And many times a person that develops a model, they are real experts on how it works, and they try to then tell other people that they should use the same model, but it may require a significant amount of effort for another person to learn everything that the person that developed the model had to learn in developing the model. And so the ease of use of a model is very important in making a selection as to whether it'll be usable or not. Are data available to actually apply the model? And if you're not able to find the data that's required, then you're not going to be able to apply a particular model to the application that you have. And then is the model going to do calculations on a scale that will actually show the sensitivity of changes that you want to try to test for? So for instance, if you have a 5 square kilometer watershed and you want to see whether or not putting in a saturated buffer in one part of the watershed that maybe covers or represents 10 acres of land within that 5 square mile area. Certain models would actually be able to pinpoint that location of that best management practice, be able to simulate the process of that best management practice. But generally more lump parameter models are not going to be able to do that. And in that case, A lump parameter model is not going to be able to show the sensitivity that you're looking for. So you want to choose a model that's going to provide that, be sensitive to the changes that you're going to implement. Some of the parameters that are needed for watershed models are listed here, or the inputs as well as parameters. So weather data, of course, rainfall and evapotranspiration, the time scale of this, whether you want daily, monthly, annual values, depends on the character of the model. Soil type distribution within the watershed is very important. In some cases, you can use more average conditions of the soil within a watershed, so more lump parameter models would probably use more averaging of soil properties. The distributed parameter model is going to want to have input on the details of soil series coverage across the watershed to be able to represent the variation in soil characteristics. Groundwater aquifer characteristics. Some models do not simulate aquifer groundwater flow processes and interaction of the surface water with the groundwater. So those types of models will not require groundwater aquifer characteristics. However, more and more models that are coming out now for use in water quality analysis and hydrologic analysis do have the groundwater component in them, and it's necessary to have groundwater characteristics. Land surface elevation. Digital elevation models are becoming more available. The whole state of Minnesota has now been mapped with LiDAR, so one can come up with land surface elevation data at very high resolution. Vegetative cover. This kind of information is readily available from satellite imagery and also from observations from the ground. Stream channel network and channel cross sections. Well, certainly stream channel network information is more readily available now that we have LiDAR data for the entire state of Minnesota. Channel cross sections can also be derived from that LiDAR. In many cases, the channel cross sections are derived by going to the field and using survey equipment. But in areas where there's not any heavy, if the vegetation cover is not heavy, it's possible to use LiDAR to come up with stream channel cross sections. Where there are hydraulic structures, culverts, bridges, and so on, that's not always information that's readily available. This is very important because the effect of hydraulic structures on the flows, interruption of flows in channels. The characteristics of soils, I already talked above about soil type distribution. Generally, soil types also have soil erosion characteristics associated with them, but this information is necessary if you want to be able to model soil erosion. And there may be other items as well. So there could be, depending on what the particular need is, there may be other parameters that are necessary for input to the model. So here are some steps involved in model selection and application. All right, so you need to consider the objectives of your analysis. What do you want to be able to accomplish? Define the questions that the modeling will be used to answer. Are you trying to figure out how much change in flow will occur, let's say as a result of land use changes that have occurred? Are you trying to find out what effects there will be or how much benefit there will be from stabilizing a stream channel or a bluff in a watershed, the effect that that might have on water quality downstream? You need to be able to specify what the objectives are to be able to select your model. Once you've done that, then you select the model that will meet that will address those questions. You then set up the model, and setting up the model means to define the geometry of the area that you're interested in. Also, input the parameters associated with the hydrology and the chemistry and also biology associated with the model. And then once you've done that, then you test the performance of the model. If you have field measurements of flow, solute outflux from a watershed, you can then modify the parameters that you input the model to be able to match as best as possible the modeled results with the observed results, and this is called calibration. And once you get a good match, you can then use the calibrated model with an independent data set to verify that you're able to simulate the independent data set. And then we can apply the model and interpret the results, and then if you have let's say you input some BMPs, that sort of thing, into the model, you can then determine as to what effect the BMP will have on the output, either in terms of the hydrology or the water quality. Some available models. This is a very big list of models that are available. The AGNIPS model, for instance, the annual AGNIPS basins, just reading some of those, the acronym that's given for each of these models, the source, who developed it, where it was developed, and then the type of model, whether it's a grid-based model or a more lump parameter model, the type of complexity, the time stepping, is it sub-daily, is it daily, monthly, or annual? The hydrology, does it only simulate surface hydrology or subsurface hydrology? The water quality parameters that the model will actually simulate, and then the types of best management practices that are allowed or accounted for in the model. And you can see that the individual cells in this table indicate whether or not the model has that capability or not. The types of water quality parameters that are supported by some of these models. I'm going to use SWOT as an example. So if you look at the last, next to the last column, the SWOT model will provide daily values of total phosphorus. It'll provide daily values of total phosphorus concentration, total phosphorus load, provide both total nitrogen load and total nitrogen concentration, nitrate concentration, and so forth, all the way down through chlorophyll A. It will not simulate algal density. It will not simulate net total suspended solids load. And you can look down through the column here to see what the capabilities are for SWOT and then for some of these other models. And we have to recognize that this table was produced a few years ago, so some of these models have been updated and may at this time be able to simulate some of these things that currently are not facilitated by a particular model. And then the types of land use or land characteristic features that are supported by different models. For instance, SWOT will allow for incorporation of urban areas, also rural areas, agriculture, forest, and the types of representation are either a lot of detailed representation, or there may be some limitations to their representation, or the degree of representation may be very limited, or it might be that not represented at all. So, for instance, SWOT does not account for estuaries or coastal areas, as an example. It does not do air deposition of pollutants either. Again, some of these features may be represented in newer versions of the model. The characteristics or the need each of these models for how much experience is needed, the time needed to make an application or to learn how to use the model, the data needs, the amount of support that's available if you need to ask somebody questions, the software tools, and the cost, if there is a cost, are all outlined in the summary of this table. So SWOT, for instance, requires moderate training, time needed for application. There's limited training that's required to learn how to use the model. The data needs are not the data needs are medium for the SWOT model. Software tools that are available are very high, so SWOT can be used, for instance, with ArcGIS. There's a thing called ArcSWOT that allows you to implement the model very readily, and the cost is the model is free. The only thing would be is if you're using ArcGIS, there might be a cost using ArcGIS, but SWOT itself is free to use. So you can look at some of these other models and see what the experience that's required, the time, how much time it needs to make an application, the data needs, and so forth for this set of models. I don't have the summary for many of the other models that I had in the list of the table that had the large list of models. But these models that are shown here are the ones that are most readily used, or the ones that are most commonly used for TMDL assessments.